Sasha and Suzanne, thank you so much for inviting me. Yeah, I'm just going to try to talk about some basics, and I'll try not to speak too quickly, but I feel like it is a short time to explain some things. But so before I really get into it, I just want to give the main result first, which is that it's really easy on a sort of basic level to understand why rifts can be narrow, just because you thin the lithosphere and it becomes weaker, and you thin it some more where it's weakest and it runs away. Classic kind of necking. But it's harder to explain what resists weakening to make wide rifts. And so I'm going to talk about a couple of ideas, really three ideas, and not in great depth, but try to lead you through what people have thought about. Just to tell you what these are, this is just a perspective view of the Red Sea from essentially Gulf of Aden, Triple Junction, the FR, on up into the very, very narrow Gulf of Suez, 2,000 kilometers away. But the main point is these rifts can be narrower than 100 kilometers, whereas some wide rifts can be 1,000 kilometers wide. So the basic idea that I just mentioned about necking, it goes back to a number of people, but to some extent, Mackenzie made a lot of hay out of this, thinking about how stretching and necking might thin the crust, but particularly for strength-wise, thin the thermal lithosphere or mechanical lithosphere, but defined as being the cold area that's strong. And therefore, it just continues. So from the top start to a sort of middle level, stretched a little bit. I'm trying to indicate a yield strength envelope at the right, which I won't go into now. Most people are probably familiar with, but integrating the sort of stress required for deformation with depth gives you an idea of the whole total strength. And the idea is that its strength at the center of a rift goes down and it stays very narrow. Okay, well, clearly something has to produce a region of extensional deformation over a broad area that produce horse and graben. And the first thing I'm going to talk about is the idea about strength and temperature. So I call this idea, that goes back to Phil England, 1983, I believe, calls it cooling to strengthen. And the idea is still, well, it's based upon the somewhat controversial idea that the material making up the mantle is intrinsically stronger over a significant range of temperatures. So at temperatures where crustal material might flow at very low stress differences, the mantle might be quite strong and be brittle in deformation and deform at very large stress differences. And that's sort of part one. And part two is that if you have stretching that's slow enough to allow cooling to basically take the mantle that you've added to the, that sort of replace the crust and make it cold and strong. So it's based on this idea. This is a little bit complicated yield strength diagram, but just that a crustal material like quartz could be intrinsically weaker, could flow for a given geotherm at very shallow depths, whereas olivine, a constituent in the mantle, might be considerably stronger. Okay, and the idea is that if you stretch very, very slowly, you're essentially replacing the crust with mantle, and you're doing it so slowly that the mantle can thicken where it's been pulled up. So it's been mechanically thinned, but then thermally thickens. And so the idea is that the strength actually could go up. And the problem with this is that it only seems to work at incredibly low strain rates. And most rifts, most wide rifts don't extend super slowly. So this doesn't seem to work. And the person who first really pointed out a terrific problem with it about this slowness was Dale Sawyer, whom unfortunately we lost last year. He died, but a great scientist. And he made it very clear that one assumption in England's approach was that the brittle mantle was effectively infinitely strong. And if you just put in finite strength, it made the strain rates that were required to get this kind of strengthening really out of bounds for most situations. All right, the second idea I want to just quickly mention, and it may play a bit of a role in wide rifting, but probably not terrific, is related to boudonage. And so these are classic boudins, sausage structures in rocks. Here's a very grainy picture of a person for scale for this picture, but they happen at a range of scales. And the classic treatment of boudonage that seems to work to understand periodic deformation, this is essentially the extensional inverse of folding, is that viscous resistance to localization. That a somewhat brittle rock layer wants to deform in a very localized way, but it's resisted by viscous stresses, and a period, sort of a spacing comes out of that. But it really looks like, even though you get some structures that are amazingly like, so this is sort of a laboratory experiment, I think, or a rock, I'm not sure, of boudonage, it's likely that gravity is more important than viscous. And I can't go into that in a very short talk. So it leaves us with the only thing left pretty much is gravity, or you could say crustal buoyancy is one way to look at it. And gravity is related to topography, but also at the surface, but also topography at MOHO, thinning of the crust. And you can break those apart or put them together as you like. But essentially the idea is anywhere you've thinned the crust, you actually have to do more work to continue thinning. You have to pull material through a gravity field out of a sort of potential low in that. And this is the most complicated figure, and there's too much going on in it, but I just want you to take away two little things of it, just little sketches. This sort of sketch is saying for the thickness of the brittle lithosphere, the classic yield strength problem, this whole idea that I explained before, if you thin the lithosphere in one area, effectively you've weakened that. You've lost this gray area of stress, or the integrated part that would be a force. But likewise, if you thin the crust, you change the pressure distribution. This is just an isostatic crust. And it's interesting, the scaling works out to somewhat the same. Forget about all these little extra numbers that come in. But essentially, the force change depends on the square of the lithospheric thickness or the square of the crustal thickness. Anyway, it looks like, and the key is the yield strength can be quite high, but the buoyancy force is just limited by gravity, density changes, and thickness of crust. So one thing that happens is if you have thick lithosphere, the yield strength variations completely dominate over buoyancy. So that, again, is a takeaway. I can't go into great detail here. But if you put it together in the simplest possible way, and I sort of threw this all together in a paper 30 years ago, that if the region you're thinking about is cold and the lithosphere is thick, then you really expect the dominant effect to be this yield strength reduction. And actually, if the lower crust is extremely hot and weak, so it can flow easily, you expect to get localization, again, due to pulling up isotherms and thinning the lithosphere, and it might produce something we call a core complex. In between is really dicey whether you actually get this to happen, that you can have something that's weak enough that the buoyancy force dominates, but not so fluid, or the crust not so fluid, that it flows and essentially wipes out any topography on the MOHO. And so just to mention, I hope Donna talks a little more about core complexes, but core complexes are essentially localized rifts within wide regions of rifting. And they're an interesting topic in themselves, but we won't go into great details. So one thing that came out of that 30-year ago study was that it really is hard, even in simple models and complex models, to get wide rifts. And for some crustal rheologies, if you make it too strong or too weak, you won't get any region that would predict a wide rift. So these are predictions of a series of models in terms of crustal thickness variations initially and heat flow variations. It says, okay, there's a region, I think this was for a dry quartz crust, and it sort of matches some places, the basin range. The idea that thick crustal areas like Tibet or the Altiplano might be areas that would form core complexes when they extend. Anyway, so to get really hot, thick crust, and I think Donna's going to talk more about this, you really probably need to orogenically thicken the crust. But the big takeaway is you can't have things too hot to break in a distributed way, or you kind of get rid of the buoyancy effect, or a large part of it. Okay, I want to bring up two other things really quickly. I think I'm out of time.
Yep.
So, and something to spark some discussion that maybe we'll have to spill over after this session. You know, this sort of, I've always thought this sort of mode that Sasha wrote about 6 or 7 years ago was a little different than these. I always think of it as a sort of an eating into the lithosphere. And I would love to do some more analysis or have someone do this and figure out how much essentially the cooling problem becomes much more viable when the lithosphere is very thin. The time constant goes with the square of the lithospheric thickness. So it would be very interesting to know if a kind of very hyperextended crust, whether that's a wide rift and what it's related to. And Sasha maybe knows all this already. And then the last point is that actually I've been trying to push Arthur Olive to do this for a while. Maybe Arthur's on this, so I can push him some more. So he wrote a wonderful paper a few years ago showing that just worrying about the surface processes, the gravity effects near the surface, that erosion and sedimentation could affect the pattern of faulting, and focus more on getting, rather than antithetic, synthetic faults. Now, nobody's put this into a model that gives you a wide rift that I know of, but it is pretty clear that the data indicates that wide rifts are full of synthetic faults. Okay, I'm done.
Thanks, Roger. That was a quick ending.
Yeah, boom.
So we have a couple of minutes for questions. Who wants to start? Please type them in the chat. Cindy has the first one.
Let's see, can you read it? I don't.
Well, ideally, Cindy unmutes herself and then asks it herself. That makes it more fun.
Hey, Roger, great to see you up so early this morning.
Oh, it's not that early. Okay. Nice to hear your voice.
No, I just wanted to provoke you to talk a little bit more about a different type of a pseudo wide rift that actually is narrow and migrating magmatism. So time variations in strain patterns and artificial artificially wide rifts, because they're not synchronous, asynchronous strain, particularly in the presence of magmatism.
Whoa, you're.
Yeah. Well, you know, your SDR paper and the requirement that everything jumps around. Yes.
Oh, okay. So I was trying to keep this simple, but okay, let's get complicated if you want to. So I think what Cindy's talking about is maybe two things. One of them is that when you have magma introduced into the system, as many people have worked on and know, and you can see in geology that magma can affect rifting, can be affected by rifting, but certainly active magmatism may help initiate rifts. So I think the particular thing, so that's the broad thing, and that's a lot to be said about that. But in the South Atlantic, where we have such fantastic data, actually, largely because of a big German program there a number of years ago, 10 years and 15 years ago, there's an interesting pattern of volcanics that I think might be explained by the center of magmatism migrating in a particular way. But that's all I can say without figures, I guess. That's a possibility in some areas. I mean, you see it on Iceland, and I mean, it's not a radical thing. I mean, I keep checking every morning to see if the Reykjanes Ridge is actually finally erupted, but the center of it. But you know, there's migration of the center of volcanism happening right now from the Western Rift to the the Eastern Rift. And it's happened several times in the past 15 million years of formation of Iceland. And there are various reasons why magmatism may migrate there. It's probably that you have a relatively fixed plume and the ridge is migrating over it.
Okay, thanks. Yidu Liu has a question. Suzanne, sorry, but you are convener. You get only to ask your questions when no one else is asking questions. Yidu, do you unmute yourself and ask the question yourself?
Oh, sorry. Yeah, thank you for letting me. I also thinking you're going to read the question. I'm just wondering if there's any updated view since your 1993 paper about the role of strain rate on the formation of wide rift.
Oh, on strain rate. Oh, I mean, I have not done a lot on that. I'm not sure if others have done more. Yeah, the fully numerical models of these 2D numerical models that produce details. I mean, like the details I'd love to see, like maybe faulting patterns and things. They're difficult to run and there are a lot of parameters. So no, I'm not aware of too much more work specifically on the strain rate problem. That's an interesting question. But certainly, I mean, we know roughly how fast the basin range has been widening, how fast the Aegean has been widening, and they're not in incredibly low strain rates. I'm not sure if there are good examples. Maybe Donna knows low strain rate areas.
Okay, thanks. Then the last question by Suzanne. Finally.
Hi, Roger. Thanks a lot
Hey,
for the presentation. So you showed the different modes of rifting in continents, huh? So before breakup. So could you say something what your thoughts are about the link between, say, the wide rift that develop in continental rifting versus what they look like when they become a rifted margin? So my feeling is that this is not a one-to-one correlation, that a wide continental rift does not necessarily produce a wide continental margin. What's your about this?
Yeah, no, that's a very interesting question. No, Rob Bialas, who's a student of mine, worked a lot on taking sort of areas of thick, kind of orogenic, super simplified numerical treatments of thick crust that might have been conceivably orogenically thickened, and pushing them to break up. And I guess, I mean, the interesting thing is you do see these sort of patterns that you can go from a wide rift to a narrow sort of rift without, I think you're absolutely right. And it may depend on some details of rheology and the exact thermal conditions, but typically those models, and John Hopper worked a bit on this, I guess, and you can certainly get a sort of a transition as the crust thins to a sort of a narrow margin. That's certainly quite possible, at least theoretically. And you know, that presumably happens. The Ross Sea, I guess, would be a good example of an area that apparently has some broad basins that look like they extended over a wide region, and then clearly it pinched off at one point, and New Zealand broke away. But yeah, hopefully somebody's working on all this. I am actually not doing that much with models right now exactly of this type.
Thanks a lot. I think Sasha's giving some hints here.